5C is about histograms. You probably think of histograms as bar graphs. We know that sometimes if we're visual learners, if we can see it in a picture form, it may make more sense to us than just looking at a table full of numbers. All right, this is our frequency table we had from the previous lesson. The left column was the ranges of miles per gallon for different mini compact cars, and the second part's the frequency. When we make a histogram, we draw bars with the heights for the frequency. The range from 18 to 20 with a frequency of 3, we'd have to go up to where we think 3 is. Oh, well, we have to number these. 4, 6, 8, 10, 12, 14. We don't go past 14, so I'll stop there. So there's our bar graph. I'm going to kind of shade it in a little bit. This basically means up to, but not including 21. So this range actually does include 18, 19, and 20. If it was something that was in between, it would include everything up to, but not including 21. The next bar will include everything from 21 up to, but not including 24. We notice here that was 3 again, so we draw another bar the same height. I'm going to kind of color it the other way. 24 to 26 was 14, so this one's going to get a good bit taller. There's 14. I'm not even going to bother to color that one in. 27 to 29 is 13, so we go all the way up to 13. 30 to 32, that was really short, just 2. 33 to 35, we go back up to 13. And 36 to 38 goes to 3. So there's our histogram. You can see that even though we kind of drop down here between 30, 31, and 32, that the majority of mini compacts have mileages between 24 and 35. All right, the other thing we learned to do last time was we did a relative frequency. I don't know if you remember, if we put this, we added this up, we got 51, and then to get the relative frequency, we would do 3 over 51 times 100%, and we could fill in those percentages. I'm going to fill those percentages in with some whole numbers. I'm going to do 3. I'm going to round to the nearest whole number of percents. So 3 divided by 51 times 100. If I round that to a whole percent, that's 6%. 14 divided by 51, that's 27%. 13 came out to be 25%. 2 was 4, and 25 again. Notice if I add all these up, these are percents, I would expect to get 100, but in truth, I only get 99. And that's simply because when we rounded the numbers, all those little tenths that we cut off would have made up that last percent. When I rounded to the nearest tenth before, you'll remember we got like 100.1%. So anytime there's rounding, could be a tiny bit off from 100%. So Let's fill those numbers back in over here. That was 6, 6, 27, 25, 4, 25, and 6. And all of these were percents. Oh, oops. So I can fix that for us. Did not mean to get that carried away. All right, so let's draw our histogram. We're going to need to decide how to number this vertical axis. We need to go up to at least 27. And I think I only have 10 lines, so I'm going to count by threes. 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. And these should really be labeled, at least with a percent sign, so that people know that that's a percent. All right, 18 to 20 is 6%. So there's the first bar. 21 to 23 is another 6%, so the second bar is the same size. 24 to 27, I need to go all the way up to 27%. So I hopefully can kind of go straight up. There's 27. And there's that bar. 27 to 29, I need 25%. Now this time I'm going to have to do a little bit of an estimate. 25 is not on the bar, but it should be 1/3 of the way. There we go. 30 to 33, or 30 to 32 really, was 4%. 33 to 35 was 13%. So we go back up, I'm not 13%, 25%. So we go back up to 25. And then finally, the last 36 to 38 was 6%. So there's our histogram representing the relative frequency as opposed to a histogram of the frequency. Notice in this case, they have the same shape. If we go back, the shape is the same, but the numbers are different. So we get the same visual picture when we graph the frequency that we get when we graph the relative frequency. It says create a third histogram using frequency table below for the same data, but with bins of size 10 instead of size 3. Well, when we did our bins before, I have that data so we don't have to recount all of that. There were 11 in this range, 32 in this range, and 8 in this range. So we need to be able to get up to 32. So we can count by threes again, I believe, and kind of squeeze in, whoops. See if we can squeeze in our numbers here. 9, 12, 15, 18, 21, 24, 27, 30, and 33. All right, 15 to 24 has a frequency of 11. So we need to go up almost to 12, not quite, 2/3 of the way through that last graph. Here we go. 25 to 34 has a frequency of 32. It's going to be really tall. Let's see if I can. So we're going to go all the way up here past 30, 31, 32, about right there. Now I could have numbered this slightly different to make it fit a little better if I wanted to, but and then 35 to 44, we had a frequency of 8. Okay. So again, you can clearly see here that the peak is occurring between 25 to 34. All right, in part D, we're going to actually look at the shapes of distributions. And to do that, we're going to start first by looking at a new type of graph. It's called a dot plot. Each symbol on the plot represents a count for that measurement. For example, there is one person with a heart rate of 60 beats per minute and 2 people with a rate of 100. So you can see right here, that triangle, that represents one person that's getting 60 beats. Notice though, over here at 100, there's 2. How would you describe the shape of this graph? You think about it, but if we look at it, it looks something, not exactly, like this. This is commonly called a bell curve. Lots of statistical data, but not all of it, will have the shape of a bell curve. What does this graph tell us about the adult heart rates? Well, just looking at it, we can pretty much see that the typical heart rate is 80, and from 60 to 100 would be pretty much the normal range. There's a few out here, and there's a few out here, but those seem to be outliers. Those don't seem to be normal heart rates. So what we're going to do in this lesson, we're going to look at dot plots, and we're going to look at the shape of distributions. What's the data look like? So consider this dot plot. Read it carefully to determine what the symbol means. All right, each X is approximately 1 million households. The horizontal column gives us the household income. Okay, right here is $50,000. Here is $100,000. That one's at 150, and this is over 200,000. It says data is rounded to the nearest thousands place. The bin size is 5,000. So 50,000 means 50,000 to 54,000. All right, so this first column right here, if the bin is, that group had an income from $0 to $5,000. That'd be up to 10,000. I mean, this would be 10,000, 20,000, 30,000, 40,000, 50,000. So you can kind of see how it breaks up. It says there is also approximately 5 million households with 200,000 or more. So out here, there is, if we do everybody out here, 200,000 or more, there would be 5 more exits, but they might be really spread out. We don't know where we would put those. There may not be 1 million between 2000 and 2005, so those increments might be really small. What does the overall shape of the dot plot tell you about household incomes in the United States in 2011? Let's go back. Just looking at it, we could count those dots. I don't know how many there are, but to me, it looks like, just roughing it out, that the middle might be somewhere around here. Where do half the people, let's count these X's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've lost my place. 17, 18, 19, 21, 23, 25, 27, 30, 33, 36, 39, 43, 47. I'm counting about 47 X's over here. There's 4, 8, 14, 20, 26, 31, 37, 42, 47, 51, 55. So that's 55. So actually I'm a little bit off. I probably need to scooch over here. If I get somewhere around 50, you can see that's kind of in the middle. We forgot these 5 dots. That actually we were probably right before. If we add those 5 dots, there's about 52 people that make, 52 data points over 55,000. And I've got 55 that's under that 55,000. So you can see the median, the one in the middle, somewhere around 55. That's one of the things we can see. What's the average household income? How would you describe the shape of the dot plot? Okay, you can see we actually have more data points to the left than we have on the right. If we just look at it. This is described as being skewed right. And you go, but Miss Hughes, there's more points on the left, and you're true. That might not seem obvious. Skewed right means that if you find the peak of the graph, and here's the peak way up here. See how these all have, that's the highest point? If you find the peak, the average is to the right of the peak. Another way of thinking about it, when you are skewed right, you generally will have a long, they call it a tail. Think of a tail to the right. So we have a lot of data over here on the left, and we have this long tail to the right. But when we have a long tail to the right, you might consider this point the most frequent up in here, but this is closer to the average. I'll draw you a picture of that here, maybe in a slide. What does the overall shape of the dot plot tell you? All right, when you have a plot and the shape of it looks like this, when your peak is here, but you have a tail, you see how this part almost looks like a bell curve? Your average or your mean is over here. We call this skewed right because it means your average or your mean is to the right of the peak. If you have a graph and the data looks like this, here's your peak, but your average value would be someplace over here because of all this additional data. That is called skewed left. Okay. Notice it's a little bit opposite. There's a tendency to want to think this is skewed left because the peak is on the left, but it's skewed right and that simply means the average or the mean will be to the right of the peak. So you'll have that long tail to the right. When you're skewed left, you'll have a long tail to the left, and that average or that mean value will be to the left of the peak. Look at the relative frequency histogram for the fuel economy of 2013 diesel vehicles. How would you describe the shape of this? You might describe this one any way you want to, as being perhaps V-shaped. Sometimes you see something that has two peaks, which this seems to. We have a big peak over here, but it also seems to peak over here also. All right, measures of central tendency. I suspect most of you remember these from school. We have three common measures of central tendency we want to talk about. It says, imagine that a sample of individuals report the balance on their credit card. The histogram summarizes this report. How many individuals are included in the frequency? So we have to just add them up. Notice we have 2, 2, 4, 5, 4, and 3. So if I add 2 plus 2 plus 4, that's 8, 13, 17, 20. So there's 20 people in this sample. All right, so we're going to look at understanding the difference basically between mean and median, and how to just how conclusions derived from statistical summaries are subject to misinterpretation. That's a very common problem in the media. Statistics are often used to mislead the public. And histograms are graphical displays useful for showing the shape of a distribution. It says, which bin contains the median credit card balance? All right, we haven't defined median yet. So, mean, median, and mode. Let's start with median. Median means middle. If you have an odd number of data points, you can get the middle value. If you have an even number, it's the average of the two middle values. Here we have 20 data points. If you have 20 data points, let's just look at 20 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If you have 20 data points, these two will be the middle. There's 1, 2, 3, 4, 5, 6. There's 9 points below, and there's 9 points above. So we would think of the median being the average of whatever those two are. So let's just see. Here's the first two. Here's the next two. So if we go all the way from here, that's 4 values. Here, this is 8 values. Tell you what, I'm going to relabel that. I'm going to make it a little clearer, I think. Let's go back. Okay. think of this as being 1 and 2. This is 2 more values, so this is 3 to 4. This is 4 values. This is 5 to 8. This is 5 values, so this is 9, 10, 11, 12, and 13. This is 4 more values, so 14, 15, 16, 17. And then finally, this is our last 3 values, 18, 19, and 20. Okay. You can see in this case, the median value, the middle value, this 10th and 11th data point, are in this middle column. So, which bin contains the median credit card balance? The bin from 7,500 to 10,000. I don't know exactly what it is, but I know it's in that bin. That bin contains the 2 middle data points. It says create a data set that matches the histogram. In other words, record a set of dollar amounts and including 2 values ranging from 0 to 2,500 and 2 values from 2,500 and so on. Then compute the mean and the median of your data set. All right, this is kind of a big project. We're going to try and do it. We're going to have 20 data points. So let's just start. We need 2 from 2,500, under 2,500. So the first person, I'm just making these numbers up. Somebody owes 900, somebody else owes 2,100. That takes care of those 2. That's 2 between 0 and 2,500. Someone owes 2,550, and somebody owes 2,800. There's 2 values. So we've done those 2 values, those 2 values, those. Now we need 4 values between 5,000 and 7,500. So 5,100, 5,700, 7,100, and 7,350. Those all 4 are in that bin. There's 5 values in this next bin, more than 7,500, so 7,500. So exactly 7,500, 7,600, 8,500, 9,300, 9,900. Those 5 values all fit in this bin. We still don't have enough. We have to keep going. We want 4 values over 10,000. 10,100, 10,800, 11,000, and 12,000. There's 4 values for that. And then our last bin is between 12,500 and 15,000. So 12,800, 13,000, 14,900. Well, let's make that 14,800, 14,900. So there's our last 4. I kind of put brackets to show you each of the bins. You could have made up completely different numbers, but I just said make up some numbers. Mean is and median. The median is going to be the average of the 10th and 11th data point. So let's count our data points. 1, 2, 3, whoops. Oh man, it better not have erased that. Nope, didn't. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14, 15, 16, 17, 18, 19. How did I get one too many? Oh, this last one's only supposed to have 3, and I put 4. So we just need to erase one of those. We'll go back to my original thought, which was, had it right to begin with. We'll just have 14,900. All right. So the two middle values are these two. Let me change colors. 10 and 11. If I want the median, I take my two middle values and I get the average. 7,600 plus 7,600 plus 8,500 divided by 2. 7,600 plus 8,500 divided by 2. And I get 8,050 is the median. So when you're looking for median, you're looking for the middle. If there are an even number of data points, then you need to look for the two middle points. Add them together and divide by 2. So let's write down median $8,050. Now, to get the mean, that's what you guys think of an average. All we do to get the mean, and I'm going to need a little more space, I'm going to erase a little bit of this. I need to add up all the data. So it's the sum of all the data. So if I add up all of these points divided by the number of data points. So in this case, let's just start 900 plus 2100 plus 2550 plus 2800 plus 5100 plus 5700 plus 7100 plus 7350 plus 7500 plus 7600, 8500, 9300, 9900, 10,100, 10,800, 11,000, 12,000, 12,800, 13,000, 14,900. If I added up all those data points we made up, I get 158,700. And I need to divide that by 20. When I do, I get 7,935. So our mean was 7,935. That's what I get when I just average up all the data. So median means it's in the middle. Mean means it's the average of all the amounts. All right, here they've given us a definition. The mean is the sum of the data divided by the number of the data. And they got 8,100. Median is the one in the middle of an ordered set of data. Since we have an even number of data, in this case, here's our data, 1,000, 1,000. They picked really easy numbers, similar but not the same as ours. They added all that data up. They got 162,000 divided by 20, 8,100. We got 7935, I believe, for ours. Median is the one in the middle. Since there's an even number, the median is the mean of the two middle numbers. In this case, the two middle numbers were 9,000. So the median was 9,000. We already computed mean and median of our data set. Mark the mean and the median of your data set on the horizontal axis of the histogram. So on the horizontal axis, we got 7935. Let's see, we can divide this up maybe. So 8,000, 8,500, 9,000, 9,500. So we got, our mean was 7935, and our median was 8,050. They were very close together. There wasn't a big difference between our mean and our median. Which phrase best describes the median of your data set? Significantly less than the mean, roughly the same as the mean, or significantly greater than the mean? Our median was roughly the same. We had 7935 for the mean. We had 8,050 for the median. So we were not very far apart. Here's a different graph. You notice this graph, it looks like it might have a little bit of a tail. The peak is here. We have a little longer tail over here to the left. So it might be slightly skewed to the left. What does that mean? Well, it means that our average value is probably to the left of our peak value. It says, imagine another sample of individual credit cards balanced by this histogram. This one looks really interesting. Notice the median is 0. The mean is 2,600. This is definitely right skewed. What does this mean? How can our median be 0? Well, look how many data points we had. We have 14, 2, 1, 1, 1. We still have 20 data points. If the median is 0, the first 11 data points must be 0. That's actually good. That means they surveyed 20 people, and of those 20 people, 11 owed no credit card debt. So that when you averaged the 10th and the 11th data points, you had an average value of 0. Okay. However, when you averaged all of the values, you got a value of 2,600. That doesn't mean there was one person over here that still owed somewhere between $12,500 and $15,000. Each of these people owed more than the mean. However, the median was very much to the right. It says, interpret the median for this sample is $0. Interpret this statement. What it means is more than half the people owe $0. It really could have been even more than 11. Anytime that for the median to be 0, for the middle value to be 0, the only thing we know is when we list them all out, they'll start owing money over here. But when we're at the middle, we're still at 0. More than half the people had a 0 balance. Okay, we've reached the end, so we'll stop now.